Integration by parts. Integration by parts is another integration technique, and we'll start by deriving it. The integration by parts formula can be derived from the product rule for derivatives. Here is the product rule for derivatives. The derivative of f of x times g of x equals f of x times g prime of x plus g of x times f prime of x. And what we'll do is integrate both sides. So we can see the integral taken of each side of the product rule. And on this left side, by the fundamental theorem of calculus, we have that the integral and the derivative are the inverse operations, and we'll just be left with f of x times g of x. On this right-hand side, we can integrate each term separately if we have a sum. So here I have the integral of the first part, f g prime, plus the integral of g f prime of x dx. And from here, we're just going to do a little bit of rearranging. So if we color code things, maybe it will help us see what's happening. So the integral of g of x times f prime of x, we're going to go ahead and subtract that to the other side. So f times g minus the integral of g of x times f prime of x is on one side, and then the integral of f of x times g prime of x stays on the other side. So here we have the integration by parts formula, but we recognize it using different variables. So what we do is we say let f of x be u and g prime of x dx be dv, since this represents a derivative. So the formula that we're used to is that the integral of u dv is equal to u times v. So g of x would be the antiderivative of g prime of x, so that's why it's v, and then minus the integral of v du. So again, v was g of x, and then du is the derivative of u, which was f of x, so there's my f prime of x. So this is the formula that we use for integration by parts. The integral of u dv is equal to uv minus the integral of v du. So again, here's that integration by parts formula, and we will need to analyze an integral of the form, so the integral of f of x times g prime of x dx, and we'll need to determine the parts for integration by parts. We're going to need that u, that f of x function, and that dv, that g prime of x dx function. So how do we know how to pick a correct u and dv? So here are some strategies and tips for choosing the u and dv. The u should be a function that can be easily differentiated repeatedly. The derivative of u should be nicer or simpler than u. The dv should be a function that can be easily integrated repeatedly. And if natural log x is in the integrand, we're always going to let u equal the natural log of x. Let's take a look at our first example. We have the integral of x times cosine 2x dx. Now here, if we were to try a u substitution and let u equal 2x, the derivative would just be 2, and we wouldn't be able to rewrite x in terms of u. So this is going to be an integration by parts. And now it's a matter of figuring out what are my parts. What is my u and my dv? So here in my product, I want to let u equal the function x. So x is a function that can be easily differentiated. So if u is x, then its derivative, du, is just 1 dx. So that's a nicer or simpler function than just x. I had a linear function, and now I have a constant function. And that leaves the other part of the product to be my dv. So my dv is cosine 2x dx. And this should be a function that can be easily integrated. So we can find the antiderivative, or the integral of cosine 2x dx, to get back to v. So that would be 1/2 sine 2x. So now I have all the parts needed to complete the integration by parts formula, so I'm just going to rewrite it so that we can remember. If we integrate u dv, the answer is u times v minus the integral of v du. So here, if we start with u and dv, and now we found du and v, then what we're really doing is we're going to be multiplying, so u times v together. So in my answer, I'm going to have x times 1/2 sine 2x. So that's u times v. And then we're going to have minus an integral that we still have to evaluate, the integral of v du. So here, these two pieces multiplied together. So that's going to give us 1/2 sine 2x, and then just dx, because I had that 1 dx, so just dx. So the integral that I have left, I can directly evaluate. So I'm going to go ahead and simplify the first part, or move the 1/2 to the front, times x times sine 2x, minus, so here the 1/2, the coefficient, is going to stay there in front, and the antiderivative of sine 2x is going to be negative 1/2 cosine 2x. And then this is an indefinite integral, so we'll have our plus c. So here we'll multiply this together. I have 1/2 x sine 2x plus 1/4 cosine 2x plus c as my answer. So this over here was my scratch work, my finding my u and my dv, so that I can find du and v to substitute into the formula. In this example, I have the integral of the natural log of 2x over x squared dx. Anytime I see natural log in the integrand, I want to let that be my u. So I have u equals the natural log of 2x. Du is 2 over 2x dx, which simplifies to 1 over x dx. Now I have a 1 over x squared dx, so we're not going to use u substitution. We're going to finish by using integration by parts. I still need to find a dv. My original integrand was written as a quotient, but I can express it as a product if I write it as the natural log of 2x times x to the negative 2 dx. So now I can see my dv is going to be x to the negative 2 dx. Integrating that to get v, I'd get x to the negative 1 over negative 1, or negative 1 over x. So this is all of my scratch work. So now I can apply the integration by parts formula. I'm going to have u times v, so multiplying diagonally here, I'm going to have natural log of 2x times negative 1 over x minus the integral of v du. So that is here, I'm going to multiply v and du together. That's going to be negative 1 over x times 1 over x dx. So now I have negative natural log of 2x over x plus the integral of 1 over x squared dx. Well, the integral of 1 over x squared dx is x to the negative 2, and we already did that antiderivative. That was negative 1 over x. So here, my answer would look like negative natural log of 2x over x minus 1 over x plus c. Or we can combine this to be negative natural log of 2x minus 1 all over x plus c. In this example, I have the integral of the natural log of the 4th root of x dx. Now I do see a natural log in the integrand, so I would think to make that my u, but before we do that, we're going to apply a property of logs. So we have the integral of the natural log of x to the 1/4 dx, and properties of logs tell me I can pull the 1/4 to the front of the logarithm, making it a coefficient, and that coefficient can actually come out of the integral completely. So I have 1/4 the integral of the natural log of x dx. Now I'll go ahead and let u be the natural log of x. Du is 1 over x dx. And I don't have a 1 over x dx, so this is not going to be a u substitution. It is going to be an integration by parts. So my dv is actually just going to be 1. So here I do have a product. This is the natural log of x times 1 dx. So my dv is 1 dx. So to find v, I have to take the antiderivative. Well, the antiderivative of 1 dx is just x. So now I have my scratch work set up. I can apply my integration by parts formula. I don't want to forget the 1/4 in front, so I have 1/4. I have u times v, so I have natural log of x times x minus the integral of v du. So x times 1 over x dx. So this is now 1/4. I have x times natural log x minus the integral of just 1 dx. So the x times 1 over x became just 1. The antiderivative of 1 dx, again, is just x. So I have 1/4 x natural log x minus x plus my constant c. Now, the integral of the natural log x appears so frequently that I would say it's just worth memorizing. So the integral of the natural log of x dx we just saw is x times ln x minus x plus c. We're going to go ahead and start this next example. So I have the integral of x to the 4th sine x dx. We're going to let u be the polynomial x to the 4th. Then du is a nicer function, a cubic, 4x cubed dx. dv is going to be sine x dx. So v is its antiderivative, negative cosine x. If I apply my integration by parts formula and multiply u times v, I get x to the 4th times negative cosine x minus the integral of v, that's negative cosine x, du is 4x cubed dx. Now, the resulting integral is also going to require an integration by parts. Now, I'm not going to multiply this together right now. I'm just going to go ahead and move ahead to my next integration by parts. Now, I would have to let u in this next integration by parts be 4x cubed. So notice that 4x cubed was my du for my previous problem. So I'm just going to cross that out and say, well, this is my new u from this integral. And then my dv would be my negative cosine x with the dx part. So notice that negative cosine x dx was the v from my previous integration by parts. So I'm going to cross that out, and I'm going to make this my new dv. So now if I were to apply the integration by parts again, so u is 4x cubed, so then my new du is going to be 12x squared dx, and my new v is going to be negative sine x. And then I would go ahead and multiply across my diagonal here. So I'd have 4x cubed. So let's see. I'm going to bring this down. I have this x to the 4th negative cosine x, that's still there, minus, I'm going to put parentheses, I'm going to have u times v, that's 4x cubed times negative sine x, minus the integral, and I'm going to go horizontally here, of v du, so negative sine x times 12x squared dx. So now if I look at this remaining integral, it too would require another integration by parts. And then here we would have to distribute in this negative, because there's now two terms in here. So this would kind of end up being a mess. So when we have to do repeated integration by parts, we have another method. So let's go ahead and take a look at that new method. Now we have the tabular method for integration by parts. So when trying to evaluate the integral of x to the fourth sine x dx, this is going to require multiple integration by parts. So the strategy is we still have to pick a u and a dv. So our u is x to the fourth and our dv is sine x. And we make sure and put those on the same line horizontally. And I apologize for these being kind of blurry. And then what we do is we do repeated differentiation along the u column. So I take the derivative of x to the fourth, which is 4x cubed. The derivative again, 12x squared. The derivative again, 24x. The derivative again is 24. And finally, we end up with 0 as our derivative because we started with a polynomial. And that's how we know when to stop. Then I work on my dv column and repeatedly finding the antiderivative. So the antiderivative of sine is negative cosine. Then I have negative sine, cosine, sine, back to negative cosine. So I make sure and stop when I line up with that 0. So the tabular method works by taking the first u and multiplying it with this diagonal here, the first antiderivative, so I had dv was sine x, its antiderivative was negative cosine x. So we're going to start by multiplying those two together. So we're going to have x to the fourth and then times negative cosine x. Now the signs on those stay the same. So we say this first multiplication that's taking place here is going to be multiplied by a positive 1. So the signs are going to stay the same. Then the next part of my answer is I'm going to take that next diagonal, but this time I'm going to multiply by an extra negative. So when I multiply these together, I'm going to multiply by an additional negative 1. So the sign is going to change. So it would have originally have been negative 4x cubed sine x because of this negative, but this extra negative is going to change the sign, so it's going to be plus 4x cubed sine x. And then we move down the next diagonal, and that sign stays positive. So it's going to alternate. It's always going to start positive. So it's going to go positive, negative, positive. I'll finish this out. Negative, and then the last one is going to be positive. Because the very, very last one would actually be going horizontal, and that would be an integral. But I can't, if I go horizontally here, that last one would turn into an integral. But here, if I multiply 0 times cosine, that just ends up as 0. So that's why we stop at that last diagonal here, as long as this is a 0. So now I just continue this multiplication. So the next one is 12x squared times cosine x, and it stays the same sign, positive. So I'm going to have plus 12x squared cosine x. Then I have 24x times sine x, and that would be positive, but it's going to change sign. It's going to become negative. So I have negative 24x sine x. And then finally, I have 24 times negative cosine x. So that's negative 24 cosine x, and it's going to keep the same sign. So it's going to stay negative. So it's going to be negative 24 cosine x. And then finally, plus c. So this is my answer. I didn't have to take an integral within the integration by parts formula because it was all worked out here in doing the column. So this is the same thing as integration by parts, just a different way of organizing our work. The sign changes are needed because of that idea of distributing. As we saw in that example we previously started, we'd have to distribute that negative. So that's why there are some sign changes that happen in every other product that's going on. So here, if I were to simplify my answer, I'd have negative x to the fourth cosine x plus 4x cubed sine x plus 12x squared cosine x minus 24x sine x minus 24 cosine x plus c. So this is, in this example, we're going to try the tabular method one more time. I have the integral of x to the third divided by 2 to the x dx. Now I want to write this as a product, so I have the integral of x to the third and then times 2 to the negative x dx. And I'm going to choose my u as the polynomial, so u is x to the third, and my dv is 2 to the negative x. So now I apply repeated differentiation here, so I have 3x squared, 6x, 6, and 0. And now I continually integrate this. So I have 2 to the negative x. Well, the antiderivative of 2 to the negative x is going to be negative 1 over the base natural log of 2 times 2 to the negative x. And then we do it again. We're going to get an extra negative that comes out because I have a negative x inside the exponent here. So that's going to make it a positive 1 over, another 1 over ln2 will come out. So this is ln2 squared times 2 to the negative x. So that lines up with the 6x. So my next one will be a negative 1 over natural log of 2 cubed times 2 to the negative x. And then finally I have to line up with 0. That's when I know when to stop. So this next one will be a positive 1 over the natural log of 2 to the fourth times 2 to the negative x. So here I just want to be really careful that things line up. So I'm going to adjust here. I'm going to move mine down so that I can see that each of these do line up. So now I'm going to go ahead and create my diagonals here. So the first u gets multiplied with the first antiderivative here, and the signs stay the same. And then here we're going to multiply by a negative. Here we're going to have the sign stay the same, and then here we're going to multiply by a negative. So now I just jump straight to writing this all out as my final answer. So my first diagonal is going to give me a negative x to the third. I'm going to write this as x to the third over ln2, and then times 2 to the x will also be on the bottom, because I'm going to keep that 2 to the negative x. I'm going to keep it on the bottom. So then the next one is going to be minus, I'm going to keep the 3x squared on the top, and then I have natural log 2 squared, 2 to the x in the denominator. Then I'm going to have minus, actually, because I'm going to have 6x times this negative, and then the signs stay the same, so it's going to be a minus 6x over natural log 2 cubed times 2 to the x. Then finally minus 6 over natural log 2 to the fourth, and then times 2 to the x plus c. Integration by parts with definite integrals. When I have limits of integration a to b of u dv, notice it's the same formula u times v, but from a to b, minus v du, but with limits of integration a and b. So if we're going to evaluate the integral from 0 to 2 of x e to the 9x dx, this requires integration by parts just one time. So we have u will be equal to x because du is just 1 dx. And our dv is e to the 9x dx, so our antiderivative v is 1/9 e to the 9x. So now this is going to equal, well, u times v, so notice it's that diagonal, so I have 1/9 x e to the 9x, evaluated from 0 to 2, minus the integral from 0 to 2 of v du. So that's just 1/9 e to the 9x times dx. So 1/9 e to the 9x dx. So this right here was my scratch work. So here I'll go ahead and start to substitute in the 2 and then the 0. So if I substitute in the 2, I get 2/9 e to the 18, and then minus 0, because if I substitute in 0 into this x, then the whole piece product becomes 0. So that's substituting in that first part, minus, so here we're going to apply the fundamental theorem of calculus. So the antiderivative of this would be 1 over 81 e to the 9x evaluated from 0 to 2. So here we're going to go ahead and substitute in 2 and substitute in 0. So the first part is 2/9 e to the 18 minus, I'm going to keep parentheses, I have 1 over 81 e to the 18. And this time plugging in 0 doesn't give me 0 because there's no x, that's one of the pieces of the product. So if I plug in 0, I get minus 1 over 81 e to the 0, which is just 1. So minus 1 over 81. So now we have 2 over 9 e to the 18 minus 1 over 81 e to the 18th plus 1 over 81. Don't forget to distribute the negative, that's why we kept parentheses. These first two terms are like terms, we can find common denominators, so this would become over 81 here, so the top would become an 18. So 18 over 81 minus 1 over 81 is 17 over 81 e to the 18 plus 1 over 81 as our final answer. Now we're going to evaluate the integral of arctangent 2x dx. So we actually don't have a general antiderivative for this, so we're going to go ahead and use integration by parts. My u is going to be arctangent 2x, so u is arctangent 2x, and then dv is going to be just 1 dx. So the derivative du of arctangent 2x, this requires a chain rule, is going to be 2 over 1 plus 4x squared. And then my v is going to be just x. The antiderivative of 1 is just x. So now here, when I attempt to use the integration by parts formula here, so we're going to go ahead and have u times v. So u times v. So that's, again, the diagonal here. X arctan 2x. And then minus the integral. So that's multiplying these two pieces here together. So minus the integral of x times 2 over 1 plus 4x squared. Well, so that's going to simplify to 2x over 1 plus 4x squared dx. I lost my dx over here. Sorry about that. Alright, so now this first piece is just going to go ahead and carry down. This was my scratch work. So I have x arctangent 2x, and then over here I have to solve this integral, which requires us to use a u substitution. Now, to just kind of be careful about this, I'm going to go ahead and change the variable. Instead of doing a u substitution, I'm going to do a k substitution. So I'll go ahead and let k equal the denominator 1 plus 4x squared. So then the derivative dk is 8x dx. I actually only want to get rid of a 2x dx, so let's divide both sides by 4 here. So that means that I would have 1/4 dk is equal to 2x dx. So I'm going to replace this 2x dx quantity here with 1/4 dk over, and then the denominator gets replaced with k. So I'm going to go ahead and bring down that original piece, x arctangent 2x, minus, and here I have, I'm going to bring out the 1/4, the constant, I have dk over k. So this is going to give us the natural log function, right? It's k to the first power. So we have x arctangent 2x minus 1/4 the natural log of the absolute value of k plus c, but then it's our job to plug k back in so that we have everything in terms of x. So x arctangent 2x minus 1/4 natural log of 1 plus 4x squared plus c. So this is my final answer. So this problem required us to use both integration by parts, and then the remaining integral was a u substitution, so a combination of integration technique. In this example, we have the integral of e to the x over 2 times cosine x dx. And this example, or ones like it, where I have an exponential times either a sine or cosine function, are typically called the circular examples because they have a special technique that we're going to use involving integration by parts to find them. So let's go ahead and get started. What we're going to go ahead and do is actually let either function be u and the other one be dv. So in this case, there's not really a better or worse option. Usually we want to pick the u to be a function that's easily differentiated and the derivative is nicer than the previous function, but exponentials, cosines, they're going to look very similar in their derivatives and integrals, so it doesn't really matter which one we choose. I am going to go ahead and let my u equal e to the x over 2 and my dv be cosine x dx. And then I'm going to go ahead and take the derivative. So du requires the chain rule, so we're going to have 1/2 e to the x over 2, and then when I integrate cosine to get v, I'm going to get positive sine x. So let's go ahead and write out our uv minus v du. So if I have u times v, that's e to the x over 2 times sine x minus, and then we have v du. So we're like multiplying across here basically. So I'm going to put minus the integral of 1/2 e to the x over 2 sine x dx. You know what, over here I realized I forgot the dx for the du part. Okay, so here's where we're at. We have e to the sine x, e to the x over 2 times sine x minus the integral of 1/2 e to the x over 2 sine x, lost an x there, sine x dx. The integral that I have left here is very similar to the original problem. It's another exponential times a trig function, specifically sine or cosine. So we're going to repeat the process. We're going to do this again, and we're going to let our u, but since I already have u, I'm going to call it u1. So I'm going to let my u1 equal 1/2 e to the x over 2. So the exponential function again, but I'm keeping the coefficient with it. And then I'm going to let my, I'm going to call it dv1, be sine x dx. So we're going to do another integration by parts on this piece. And so we get du1, the derivative would be 1/4 e to the x over 2 dx. And then when I take the antiderivative of sine x, I'm going to get negative cosine x. All right, so let's see what happens. We're going to bring down our e to the x over 2 sine x. And then we have minus, and here's where we have to be careful. This negative is going to have to distribute. So we're going to go ahead and apply parts again, where I have u1 times v1. So we're going to have negative 1/2 e to the x over 2 times cosine x. So I'm multiplying here diagonally. And then minus the integral of v du, or in this case v1 du1, so multiplying across horizontally here. So there was a negative, so it's going to be like negative 1/4 e to the x over 2 cosine x dx, but there's a negative here, so I'm just going to make this a positive 1/4 e to the x over 2 cosine x dx. Alright, so that's what I have. This negative would distribute to both terms. There's two different terms here. So I have e to the x over 2 sine x plus 1/2 e to the x over 2 cosine x minus, I'm going to pull this 1/4 to the front of the integral now, minus 1/4 the integral of e to the x over 2 cosine x dx. And then when you look at the integral we have left, you might be thinking, oh my gosh, I have another exponential times sine or cosine again. And we do, so we kind of went in a circle, because if you look at the original integral, we basically have that again. We have e to the x over 2 times cosine x. Just this time we have a coefficient in the front. And so that's why it's called the circular type of problem here, because, you know, we did kind of end up where we started. Now, the way that we proceed is once we get back to the exact same integrand, except of course there might be a coefficient that we pulled out to the front, what we're going to do is what I'm going to do is I'm going to rewrite it all as like one big line so that you can see sort of the little algebraic maneuver we're about to do. So I'm going to put the original problem, e to the x over 2 cosine x dx is equal to, I'm going to just copy and paste this to save some time. Oops, there we go. All right, so here's what I have. I have the original problem is equal to this line right here. Well, I'm going to add 1/4 the integral e to the x over 2 cosine x dx to the other side of the equal sign. Because I can think about how there's a 1 in front of this integral. So when I add 1/4 the integral e to the x over 2 cosine x dx to both sides, I'm going to add those numbers that are in front of the integral sign to end up with, so it's like I'm adding these two together. So I'm going to scoot up to make a little bit of space. So I have 5/4 the integral of e to the x over 2 cosine x dx is equal to e to the x over 2 sine x plus 1/2 e to the x over 2 cosine x. Alright, so we're super close to being done now. I don't want 5/4 of this integral, I just want this integral. This integral is what I was solving for without anything in front. So I can just multiply both sides by the reciprocal of 5/4 by 4/5 to get this by itself. So we have the integral of e to the x over 2 cosine x dx is equal to, so we're going to have 4/5 e to the x over 2 sine x plus 1/2 e to the x over 2 cosine x. And then we can't forget plus c, which I'm pretty sure I forgot every step of the way, but I'm at least including it in my almost final answer here. So now I have that integral that I was solving for by itself. The only thing really left to do is, just distribute this 4/5 in. So the integral of e to the x over 2 cosine x dx is 4/5 e to the x over 2 sine x plus, what are we going to have here? 2/5 multiplying 4/5 and 1/2 e to the x over 2 cosine x plus c. There we go. And so that was our answer. So you can see, we went in a circle, we got back to the exact same. Let me see if I can scroll out. It's going to be a little small to see the whole thing. Whoops. Once we got back to the exact same integrand, that's when we knew to stop and add that term to the other side to combine those like integrals, essentially. And then multiply that reciprocal to the other side to get that integral that we were trying to solve just completely by itself. So this right here, right, was all of our scratch work for those two integration by parts. Now, was there a quicker way to do this? Not really. The process is still the same, but if you don't want to do the two full u dv, u1 dv1, you could think about doing it using sort of that diagonal method, but you still have to add the 1/4 the integral to the other side. So let's kind of look at this step right here. Let's focus on this. So we could have picked our u, so e to the x over 2, and then dv is cosine x dx, and then we differentiate it once, we get 1/2 e to the x over 2 dx, and then we differentiated it again. So let's see, I'll highlight those. This is what I started with. This was u, this is my first derivative, this is my second derivative. So we have to know this is the circular problem. It's going to require exactly 2 iterations. So we have 2 derivatives, and then we started with our dv is cosine x, the antiderivative there was sine, and then the next antiderivative was negative cosine. And so we then can start to do this work with diagonals, but then once we go horizontal, that becomes an integral. So like I said, let's focus on this equation right here. So the original integral was equal to e to the x over 2 times sine x, that's part of the answer, and then plus 1/2 e to the x over 2 cosine x, and then here we're going to have minus 1/4 e to the x over 2 cosine x dx, but that's an integral. It's not just part of the answer. Whoops, and I forgot to alternate the signs, right? So this would be plus, minus, this would be plus here. Let's check that those work out. So yes, these two multiplied would be plus 1/2, and then it's being multiplied way down here times this one, right? So the 1/2 and the negative cosine with this extra negative makes it a positive. So there's where that positive 1/2 comes from. And then horizontally here, it stays the same sign, it's positive. So there was a negative and a positive, so that's a negative right there. So you could still use the tabular method a little bit, but you have to know exactly how you're using it. So normally when you do the tabular method, we stop when we get to 0 along the differentiation column, but here we're never going to get to 0. You would just have to know this is a circular type of problem. You do 2 sets of derivatives, 2 integrals, and then you go diagonal, diagonal, horizontal. The horizontal part becomes the integral, and then from there you still have to add the like integral to the other side. So definitely some options. It is a harder problem. We are reaching the more advanced integration by parts problems, but it's a good technique to remember. This next example is also a bit of a challenge. We have the integral from 0 to pi of e to the cosine x times sine of 2x dx. And this one's a bit of a challenge because it's going to require us to use 2 different techniques, both integration by parts and u substitution. If we try to go directly for an integration by parts, there's not really an obvious like u or dv situation going on here. Doesn't quite work out. And even if we went directly for u substitution, it doesn't quite work out. If I take the derivative of sine 2x, I get 2 cosine 2x. I don't see that anywhere. The derivative of cosine is negative sine x, but I have sine 2x, which is not the same thing. So actually the very first thing we have to recognize is that sine 2x has an identity. So this is the integral from 0 to pi of e to the cosine x times 2 sine x cosine x dx. This is the double angle identity for sine. And that's got to be the first step on this problem in order to get the ball rolling here. Now from here, we are going to go to u substitution. I'm going to go ahead and let my u be the cosine function, and then I can see the derivative, or almost the derivative, I could see sine x, so it's close, it's off by a negative, is multiplied in the problem somewhere. So that's going to be my u. Now to avoid confusion later, instead of u substitution, I'm going to change the variable. I'm going to use the variable k. I'm going to do a k substitution. I'm going to let k equals cosine x, and then dk is negative sine x dx. But I only want to replace sine x dx, so negative dk is sine x dx. So this problem is going to become the integral from, I'm going to ignore the limits of integration for the time being, it's going to become e to the u, e to the k, sorry about that. So anywhere there was a cosine, I'm going to put a k, and then we have a 2 there. The sine x dx becomes negative dk, so let's put the negative in the front and the dk in the back. So I replace sine x dx, and then cosine x again was k. So here's what we have. We have negative the integral of e to the k 2k dk. But these limits are x values. They are not k values. So I'm going to go ahead and turn them into k values. So k of 0, what's cosine of 0? That's 1. And then if I plug in pi, k of pi, what's cosine of pi? That's negative 1. So let's keep our scratch work separate here. That's negative 1. All right, so here's my new integral. And because I changed everything, these are all k's, it's like I can leave this behind. I can like ignore this work over here. I don't ever need to think about the x variable or the original problem again. I'm just going to move on forward with what I have left here. Now the limits of integration should be like a flashing, warning here, because it's supposed to be the smaller number on the bottom, the bigger number on the top. In order to flip them, I would need to make there be a negative in the front, so it's going to cancel with the negative that's already there. So I'm going to have the integral from negative 1 to 1 of 2k e to the k dk. All right, so here's what my new integrand is. It is going to require a integration by parts. So I have 2k times e to the k. I'm going to let my u be 2k because it's a polynomial, and my dv be e to the k. And I'm going to go ahead and do the tabular method here. So I'm going to let u equal 2k, and then dv equals e to the k dk. All right, so the derivative of 2k is 2. The derivative of 2 is 0. So I can stop there with my left column of my table. And the antiderivative of e to the k is e to the k. And the antiderivative again is e to the k. So if we do this tabular method here, this is plus, this is minus. Technically, we can always think about the last one being horizontal, but 0 times anything is 0, so that's why we really don't have to in this case. Right? So now my answer is to the antiderivative is 2k e to the k, and then minus 2 e to the k, evaluated from negative 1 to 1. So I did the diagonal, that's just the answer, right? That's the benefit of the tabular method. That's just the antiderivative. But then we're going to have to plug in 1 and negative 1, right? We're going to plug in 1 and negative 1. So let's do it. We get 2e. So if I plug in a 1 into this k, I'm going to get 2e minus 2e. So that's nice. That's just 0. Minus negative 2e to the negative 1. I'm plugging in negative 1 into this k. That makes it negative. This k is negative. And then minus 2e to the negative 1. Just so many negatives to keep track of here. So inside here, these are like terms. And so we have negative 4e to the negative 1. So we have 4e to the negative 1 whoops, which is 4 over e. Sorry about that. So this is 4 over e as my final answer here. So this one had a lot of layers to it, right? It's our trig knowledge of identities. It was a u substitution, and I chose the k variable because I knew that there was going to be a parts coming up, and I'd rather just use u and dv for parts just because of that formula. But, you know, you could have used a u substitution here, but then you probably shouldn't pick u in your parts because you don't want to have two different u's, you know, in your problem.